Welcome to this explainer where we're going to demystify the potentiometer. We're taking it from a simple volume knob and transforming it into a critical, high-precision engineering component. As an engineer, you might think you know the humble pot inside and out, right? Well, today we are going to look at the massive engineering potential hiding right inside the simple variable resistor. Okay, let's dive right into this by asking, what is the single component that makes all of these wildly diverse technologies possible? Think about it. Whether it's the throttle position sensor in a modern electric vehicle, the precise joint control in an industrial robotic arm, or even critical calibration inside medical devices and aerospace controls, they literally all rely on this exact same foundational piece of hardware.
To really unpack its secrets, we'll follow a quick physics-to-product journey. We'll explore the fundamentals, voltage dividers and rheostats, what's inside the component, decoding those tricky data sheets and specs, real-world circuit applications, and finally, we'll wrap up with the engineer's toolkit.
Let's kick things off with Section 1, the fundamentals. If we look at a basic circuit arrangement, it actually proves that physically moving the sliding wiper changes the active length of the resistor. You have a driver cell providing a known voltage across a long resistive wire. Then you've got that movable contact or wiper sliding along the track. It basically acts as a bridge, instantly converting a mechanical position directly into a proportional electrical signal. It is just an incredibly elegant solution to a really complex problem. And honestly, the math backing this up perfectly demonstrates the core physics principle behind that movement. Just look at this equation derived from Ohm's law. While the resistivity of the material, which is represented by ρ, and the cross-sectional area remain completely constant, sliding the contact physically lengthens or shortens the path the current has to travel. So as the length increases, the resistance increases. It's literally physics in its purest, most applied form.
Moving right along to Section 2, voltage dividers and rheostats.
So here is a crucial point you've absolutely got to nail, understanding the absolute difference between these two configurations. When you wire up all three terminals, you create a voltage divider. This actively scales an input voltage down, acting as a ratio. But if you only use two terminals, just one end and the wiper, you create a rheostat. A rheostat strictly restricts current flow in a loop, acting simply as a variable resistor. Mixing these two modes up is a classic design mistake that can and will burn out your components. Looking at the schematic for a voltage divider, you can see how the output voltage is developed strictly across the lower portion of the element, right between the wiper terminal and the end terminal. If the wiper is exactly in the middle, well, the resistance is split equally, and your output voltage is exactly half of your input. It's this linear, highly predictable drop that forms the basis of countless control systems we use every day.
Let's peel back the layers in Section 3, inside the component.
So what are these actually made of? Well, choosing the right resistive material depends entirely on your design goals. Making cheap consumer electronics, carbon foam might be totally fine. But if you're building an audio mixer that needs a smooth, infinite resolution and millions of life cycles, you need conductive plastic. Now, what if your circuit is sitting inside a hot, vibrating EV engine bay? Then you want the high thermal stability of cermet, which is a ceramic metal hybrid. And if you are dealing with real heavy-duty power, you've got to go with wire-wound elements, even though you have to accept a slight, stepwise resolution as the wiper physically jumps from wire to wire.
If we zoom in on the internal construction, we can see how conductive plastic is applied to an insulated metal mandrel in a helix shape. This is how you build a modern, multi-turn element. This specific design grants the potentiometer a rotational life that is orders of magnitude better than older technologies. It gives you incredible precision, literally allowing the user to turn the dial 10 or even 20 times to dial in an exact value without wearing through the track.
All right, let's tackle Section 4, decoding data sheets and specs.
Now, when you pull up a manufacturer's spec sheet, it can be pretty dense. You will frequently encounter terms like linearity and conformity, and these aren't just buzzwords. They are absolute critical metrics defining how accurately the wiper's mechanical position translates into your expected electrical output. Basically, if you turn the knob exactly 20% of the way, does the output actually change by exactly 20%? Linearity tells you your exact margin of error. When evaluating absolute conformity, you'll see how the actual electrical output, usually represented as a wavy solid line on these charts, can snake slightly above or below the theoretical straight dashed line. This happens because of microscopic manufacturing imperfections in the resistive track. And look, if you're designing a highly precise servo mechanism for aerospace, that little bit of snake in the output curve translates directly to physical positioning errors in your final product. Aside from linearity, if you're ever conducting failure analyses, you must pay close attention to power ratings and rotational life. Why? Well, because exceeding internal temperature limits will literally degrade the insulating materials and destroy the unit right on your board. Power rating isn't just about electricity, it's a hard measure of maximum heat dissipation. And rotational life is just as crucial. A part rated for 10,000 cycles might last for years in a home thermostat, but it will absolutely fail in weeks on a heavy-use industrial control panel.
Time for Section 5, Real-World Circuit Applications.
So, slider potentiometers are universally recognizable as the audio volume controls in studio mixer panels. We've all seen them. But their utility goes way beyond just sound. They provide critical linear position feedback in automated industrial machinery. Because the wiper travels in a straight line, you can mount them directly to an actuator or a robotic rail, allowing the central computer to know exactly where a moving part is at any given millisecond.
But this raises a really fascinating engineering puzzle. Let's say you have a tiny precision potentiometer rated for just 1/8 of a watt. How can it possibly be used to control the speed of a high-current, high-power DC motor without instantly bursting into flames?
The secret here is combining components. Think of it like this. The potentiometer is the brains, and a transistor is the brawn. You safely use the potentiometer as a voltage divider to adjust a tiny, low-power analog signal. You then send that signal directly to the gate of a MOSFET. As you turn the dial, the gate voltage increases, which opens the MOSFET's main channel. The MOSFET then does all the heavy lifting of driving that massive motor current, while your potentiometer stays perfectly cool and completely safe.
Let's wrap things up with Section 6, the Engineer's Toolkit.
Look, to design flawless circuits and tight PCB layouts, you absolutely must avoid these common pitfalls. A huge one is failing to derate your power calculations for ambient temperature. Just because a pot handles half a watt at room temperature does not mean it will survive inside a hot enclosure. Another classic mistake? Using a cheap carbon pot in a harsh, high-vibration environment where you really needed a sealed, IP-rated Cermet component. And if you're working with precision analog signals, ignoring contact resistance variation, or CRV, which actually causes dynamic noise as the wiper moves, is going to completely ruin your signal-to-noise ratio.
So, as a senior engineer, by systematically running through this checklist, you guarantee that you're balancing performance, durability, and cost-effectiveness for your specific application. First, ask yourself, is this a voltage divider or a current-limiting rheostat? Does the end user adjust it, or is it just a set-and-forget trim pot on the circuit board? What resolution is strictly necessary? What's the operating temperature? Answering these questions first will drastically narrow down your search when you're looking at a supplier's website. I absolutely love this advice straight from Born's Potentiometer Handbook. It is pure gold. When you are designing your circuit's thermal dissipation and current limits, always design for the absolute worst-case scenario. Assume the user is going to crank that dial all the way to the end limit, creating minimum resistance and maximum current flow. Because if your circuit survives that, it's going to survive anything. So, given how an unassuming variable resistor acts as the vital bridge between physical movement and electronic control, it really makes you wonder, what other foundational components might you be underestimating in your own circuit designs? Sometimes the most elegant engineering solutions don't come from a complex microchip, but from deeply understanding the physics of the simplest parts on your board. Thanks so much for joining me on this explainer. Keep learning and keep designing.